So this logical equivalence is the basis for another technique of proof known as proof by cases. So to prove an implication of the form P or Q implies R, notice that the hypothesis occurs as cases where either P is true or Q is true or both. So to prove an implication of this form, we prove both that P implies R and Q implies R. So let's look at an example. If n is a non-zero integer, then the square of that non-zero integer is positive. So the proof will be a proof by cases. So let n be a non-zero integer. Then this means that either n is itself positive or n is negative. So suppose that n is positive, then n squared is n times n, that is a positive number, times a positive number, which is positive. So now suppose that n is negative, then n is equal to the integer m, where m is the absolute value of n. Correction, n is equal to negative m, where m is equal to the absolute value of n. And so n squared is negative m times negative m. A negative times a negative gives us a positive m times m, which is positive. And therefore, in either case, n squared is positive whenever n is a non-zero integer. So new definition. The universal quantifier which is denoted by an upside down letter, capital A, is a logical symbol used to denote or to indicate that a specific property is true for all elements in a given domain this symbol is red for all or for every or some variation of that phrase. So let's look at an example. We look at the statement for every integer x, x squared minus 5x minus 6, or plus 6 rather, is equal to 0. This statement is a false statement. That claims that for every integer x, x squared minus 5x plus 6 is equal to 0. It's a new definition. The existential quantifier which is denoted with a backwards capital letter E, is a logical symbol. Used to indicate that there exists at least one element such that a specific property is true. The symbol is red. There exists or there is at least one or any variation of these phrases. So let's look at an example. The statement, there exists an integer x such that, and we'll use this symbol for the phrase such that, x squared minus 5x plus 6 is equal to 0. And this statement is a true statement. That claims there is at least one integer x such that x squared minus 5x plus 6 is equal to 0. So let's look at how these quantifiers relate to one another. So if we have the statement for every element x, some statement about that is true, what does it mean if we negate this statement? So if it is not true that for every element x, some statement is true, that must mean that there exists at least one element x such that that property is not true. And if we look at the statement, there exists at least one element x such that a given statement is true, and we think about the negation of that statement, it is not true that there exists at least one element x such that p of x is true. That is logically equivalent to the statement that for every element x, the property p of x is not true. Okay, so let's look at a new truth table. We'll look at the statement P implies Q or R, and the statement P and not Q implies R. So we'll build a truth table. So the first implication is true when our correction is false, precisely when P is true and the conclusion Q or R is false. So that occurs when Q and R are both false. So that occurs in this case. And in every other case, that implication is true. Now the implication P and not Q is false precisely when P and not Q is true, which means that P and Q, or rather P is true and Q is false. And that occurs in these two cases. And when the conclusion R is false, which occurs in this case. And so in this case, the second implication is false, and in all other cases, it is true. So notice that these two statements, these two implications, have the same truth values in every case. And so if we join them with a biconditional, that biconditional is always true. And so we have a tautology, and we have demonstrated that P implies Q or R is logically equivalent to P and not Q implies R. And once again, this logical equivalence is the basis of a technique of proof. Known as proof, the alternate proof by cases. So to prove an implication of the form P implies Q or R, notice that in this implication, it is the conclusion that has cases where either Q is true or R is true or both. And to prove an implication of this form, we prove the logically equivalent statement that P and not Q implies R. So let's look at an example using this technique. If an element x plus itself is equal to its square, then either x is equal to 0 or x is equal to 2. So proof. So in the proof, we're going to assume the hypothesis and the negation of the first case. So suppose that x plus itself is equal to its square and x is not equal to 0. Then we can divide both sides of this equation by x, since we are not dividing by 0, and we have x plus x divided by x is equal to x squared divided by x. And this gives us 2 times x over x is equal to x squared over x, or 2 is equal to x. And therefore, we have proved using the alternate proof by cases that if x plus x is equal to its square, then either x is 0 or x is equal to 2.